Okay, so we're live. Thanks everybody, those of you tuning in to watch our live recording today here at the Star Spot. I'm so excited to be joined here today by Professor Sandro Mereghetti. I'm going to keep working on pronouncing that better and better, but I hope that's good enough for us to greet one another today. How are you today?
Fine, thank you. And also your pronunciation was very good. Thanks.
Thank you. I hope it's getting better. Today we're going to be talking about a really fascinating, mysterious topic that's fast radio bursts. They're also known as FRBs, because I guess it's a mouthful to say fast radio bursts every time we're talking about this phenomenon. And so you and your collaborators have done some really remarkable research, and we'll talk about why it's so remarkable, why it's sort of a first of its kind, a sort of study. But first of all, we have talked about it a couple of times on the show, but not for quite some time. So what are fast radio bursts, or FRBs? How are they defined? Where do we see them? Why are they so mysterious?
Okay, from the point of view of the observations, they are defined from what we see. So they consist of very, very bright, but very, very short pulses of radio waves that arrive on the Earth. And they arrive randomly in time and in direction. So it is very difficult, let's say impossible to predict when they are going to arrive. And they are very interesting because so they were discovered in 2007. We still do not know what they are. So they are one of the remaining mysteries of astrophysics. And in short, this is what makes them very interesting.
Okay, so now the term fast radio burst, does that imply a single burst, or are we talking about some kind of repeated event, or is it like multiple quick shots, like of a semi-automatic rifle kind of, what sort of characteristics do they have in terms of that bursting?
There are a few FRBs that are seen to repeat. That means that we see them coming from the same direction, and so they have been associated to the same astrophysical object. But most of the FRBs have been seen only once. We don't know yet whether they are also repeating, but on much longer time scales. So we saw them only once. It's just a matter of waiting long enough to see them repeat or not. But it is possible that there are indeed two different kinds of FRBs, those that repeat and those that do not. And this has also some implication for the models, because you understand that if the source that originates them is something like an explosion, something that can occur only once, like for instance, a supernova going off, or two neutron stars crashing together, these are going to be just single events. The fact that we see at least some of the FRBs that do repeat means that there must be also some mechanism that does not destroy the source.
Okay, so there's a possibility, and of course we don't know enough about the origin of these to know for sure if we're talking about one particular kind of event, or maybe several different categories of events that are responsible, some for the repeating FRBs, some for the one-off event FRBs. Now let's bring in the discovery that you and your team made not too long ago, a little bit earlier this year. This was actually the first FRB in our own Milky Way Galaxy. The FRBs to date have been, I think you were saying, kind of random in terms of where we're seeing them in the sky, also random in terms of how far they are, or have these been tended to be at longer redshifts in the universe?
We know for sure that FRBs are not coming from our galaxy, at least the classical FRBs that were seen before this event last April. And we know this because we see in their radio emission the effect of propagation through a lot of material. And this effect that is measured is actually a delay in the wavelength of longer wavelengths, tell us that this light, this electromagnetic radiation, has traveled through a lot of plasma, which is much more than the one that we find in our galaxy. So based on this, we believe, and we are pretty sure, that the majority of FRBs are coming from external galaxies, not at an extremely large redshift, but still extragalactic and quite far away.
So to date, before your team's work, the FRBs had been all extragalactic, but in terms of where extragalactically they were coming from, it was at all kinds of different redshifts or different distances. Is that fair?
They were seen up to redshift of about 0.6.
Okay, so tell me about the the detection in the Milky Way. How what instruments were responsible for finding that?
Well, we first have to distinguish that there were two kinds of detection, and this is the important thing of this result, I think, because what we observed in April was we were observing with the integral satellite a magnetar in our galaxy. I will explain later what a magnetar is, okay? And we were observing this magnetar, and on April 28, we detected a relatively bright burst of X-ray and gamma rays, and not an FRB. With integral, we detected X-rays and gamma rays from this magnetar. And this is not particularly unusual, because magnetars, from time to time, they do emit these X-ray bursts. And we were observing this magnetar with integral because we already knew that this particular magnetar was active in those days. So we were keeping an eye on it, okay? The interesting discovery, which is not completely due to my team, it was a discovery made by a lot of people in many different collaborations, is that exactly at the same time and from the same direction in the sky, a radio pulse was discovered, and this was done by a telescope in Canada, which was done by the CHIME radio telescope in the Dominion Radio Observatory. So they observed a radio emission that was in many respects very similar to an FRB, exactly at the time and the direction in the sky at which we detected X and gamma rays from a magnetar. Okay, so this was the first time that an observational connection could be done by these mysterious objects that are the FRBs and something like a magnetar, which we know that they are neutron stars in our galaxy. So we establish an observational connection between magnetars and FRBs. And this came, in a sense, as a surprise, but not so much, because there were models that had been proposed for the FRBs that involved magnetars. I can explain later why this was. But this was the first time in which we had also observational evidence that there is indeed some connection between these two classes of objects that were apparently disjoint.
But even more generally than that, you're saying this is the first time that an FRB has ever been pinpointed to a particular object of any kind, that we've been able to localize it, to be able to say it's caused by or it's related to this other known phenomenon, in this case, a magnetar.
This is correct, you're right. We must say that there are FRBs, especially the ones that repeat, that in a sense facilitate the observation, because you already know that there is a source that is going to repeat, so you can organize and arrange observation. A few of the repeating FRBs have been pinpointed and localized very precisely, so they have been associated with the galaxies, external galaxies.
Right.
But we don't know what is the object, what is the model, what is the mechanism that produces them. Magnetars were one of the possibilities, and the reasons for that is that, well, maybe first I should explain what a magnetar is. Then,
sure, yeah,
okay,
let's start there.
That will make it easier to follow the argument. Okay, a magnetar is a particular kind of neutron star. And we know neutron stars as radio pulsars. Those have been discovered 50 years ago, and they are, we know a lot of them, and they are powered by the loss of rotational energy. Then we know neutron stars that are seen as X-ray sources that are powered by accretion from matter from a companion star. But at the end of last century, in the 90s, it appeared that there was another class of neutron stars that was not powered by either rotation or accretion. And after several kind of observation, it became clear that these neutron stars were powered by magnetic energy. And indeed, we now are quite sure that magnetars are the neutron stars with the highest magnetic field. Neutron stars are already extremely magnetized, billions of times fields stronger than the ones that we find on the Earth, and magnetars are even more magnetized. So the idea that magnetars could be one of the possible explanations for the FRBs comes from the following arguments. First of all, FRBs are very short phenomena. And this tells you that the sources that emit them have to be relatively small. You cannot have very large and rapid variation from an object that is too large. And neutron stars are indeed very small stars, and so they fit well in with this constraint.
Very massive, but very small in terms of volume of
yeah,
space.
they're very small in terms of volume, but they are very massive, and most importantly, they can store a lot of energy, and this was the other requirement for FRBs. FRBs are very bright, so this implies huge amounts of energy, and a neutron star, and a magnetar in particular, gives you enough energy in a small volume. So this was one of the motivation for many scientists to propose that magnetars could be one of the possible explanations for FRBs. But there were also many other models, and it's also possible that these other models are still valid. I mean, what has been found in April is just some experimental, some observational link between FRBs and magnetars. And of course, this lends support to the magnetar interpretation.
And how common are magnetars as a class of pulsars in a galaxy like the Milky Way?
Okay, at the moment, we know less than 30 magnetars in the Milky Way.
Okay.
But we are convinced that there are much more of them because the magnetars spend most of the time in a so-called quiescent state. That means that they shine in X-rays just because they are very hot, but they are rather inconspicuous as X-ray sources. On the other hand, from time to time, they become active, we say. So they start to emit bursts of X and gamma rays. And at the same time, they become brighter, but this occurs not so often. For instance, the magnetar that we observed in April this year was discovered in 2014. And that means that before then, it had always been quiescent for decades.
Right.
And since when we discovered he made, if I remember well, 3 or 4 of these outbursts. Okay, so we believe that there are many quiescent magnetars in our galaxy that have yet to be discovered. And of course, when a magnetar becomes active, they are also very interesting to observe. And this is the reason why we were observing this magnetar in those days with integral.
So now, looking at the extragalactic FRBs that we've studied previously, have we ever seen any other kind of electromagnetic radiation in addition to the radio waves? Have we seen, for example, X-rays, coming at the same time and the same frequency? So this is also the first time we've tied 2 different forms of radiation together, and of course that helps. That's another piece of evidence that it's the magnetar that is the cause of this particular FRB.
You are correct. In all the other extragalactic FRBs, X-ray or other kind of radiation have never been seen. But this is basically because of the faintness of this flux. Those are much more distant. Right. So the current X-ray and gamma ray satellites, instruments will not be sensitive enough to detect them.
Oh, I see.
In faraway galaxies.
Even if they're being put out by a magnetar in those other galaxies, we simply don't have the ability to detect those other forms of radiation.
We are able to detect them in radio, but not at high energies. And indeed, we should also be honest and say that what we observed from this magnetar is something very similar to an FRB, but maybe something different. I mean, the radio emission was a short pulse, was very bright. It resembles the FRBs, but was, of course, not as luminous as the one that we see in other galaxies. So not so much, but not as.
Well, actually, let's go in that direction, because I have read the scholarly article that you were the lead author on that made the case about the discovery of the magnetar being the link with the FRB in our own galaxy. And I think in the conclusion it was mentioned that this is very similar to the FRBs outside of our galaxy, but this one wasn't quite as luminous or quite as energetic. Is that what you were saying, or are there other differences between this particular FRB and the other ones that we're previously familiar with?
You're correct. This one was not as energetic as the extragalactic ones, but the faintest, the less energetic of the extragalactic ones are just a factor of 10 or 40 more luminous than this. Mm-hmm. So it is not so different than the faintest extragalactic FRBs.
Yeah. Well,
so it's kind of connecting the 2 classes.
You don't want to read too much into that, because you'd need them to be more energetic for us to detect them here on Earth, I would imagine. So that doesn't tell you we're looking at different objects. It's just a selection bias or a instrument bias, I guess, in this case.
Yes, if there are in external galaxies FRBs with an intrinsic luminosity like this one, they will be hard to detect them. So,
gotcha.
And the other difference is that in this particular radio emission, we see that the effect of the propagation through the interstellar medium that I was describing before are consistent with the location in the galaxy. So we don't see evidence that the light, the radio waves from this travel through intergalactic space.
Gotcha. Okay.
So this is a difference, if you want, but it's a difference with a clear explanation and a good reason for being a difference.
Right. Gotcha. Do we know enough about the theory of how magnetars function to know how often a magnetar would be an FRB or would put out a fast radio burst? And would we expect that all magnetars will do this on some kind of periodic basis?
Well, that's difficult to answer based on a single event, because up to now we only observed these ones, and of course we don't know whether what you observed is typical in a sense, or there is a variety of possibilities. First of all, we should remember that, as I told you before, magnetars are not always active. They become active and start to emit bursts from time to time. Some of them emit a burst and then go back to silence for years. Some of them stay active for a few days or a few weeks and then go back to quiescence. And we already more or less understand why there are these cycles. This happens because the magnetic field that is so strong in these objects evolves quite rapidly and makes stresses on the crust of a neutron star. When these stresses are too large, the magnetic field of the external part of the star starts to reconfigure itself. You've probably seen images of the sun when you see the flares and the magnetic fields with loops of plasma that emit UV and X-ray radiation, and you see this kind of flares in the sun. Yep. You can imagine something similar, but on a much, much larger scale. Mm. So this is something that happens when magnetars become active. And up to now, we have seen a lot of bursts from magnetars, but only in this case, we had a radio emission at the same time. So this is partly because before we did not have enough radio observation, but also now that we are keeping more attention to this, we have seen a radio emission only in this particular burst. In April, this magnetar emitted several tens of bursts, and radio was seen only from this one. Why? We don't know.
And you were just mentioning the comparison of the experience around a magnetar to that around our own sun. And I think it's worth pointing out the energies involved by way of comparison, that if I understand a fast radio burst would put out more energy in that millisecond or however much time it takes for that burst to propagate as compared to the sun's total output in 100 years, in a century of solar output. That is really incredible. That's a good way of comparing it to really get a sense of how energetic these events are, which I guess leads me naturally to ask, are they dangerous? How close would a FRB have to be to our solar system for it to pose some kind of risk to us, or would it ever pose any kind of risk to living organisms?
I think that the most dangerous effect would be not from radio waves, but from X and gamma rays. So magnetars, independent of their connection with FRBs, could be dangerous if they are very close to the Earth. Just to give you an idea, there was a magnetar that at the end of 2004 made a huge flare, a huge explosion, the most powerful ever observed. And the flux of X-rays from this giant flare, we call them giant flares because they are really giant, had the same effect on the Earth ionosphere that is caused by the solar flares. You know that the solar flares ionizes changes the ionization state of the ionosphere. And this causes, for instance, problems in radio communications, okay? So you can imagine this magnetar that instead of being at the distance of the sun was at the distance of the center of our galaxy, so tens of thousands of light years away, had on the Earth atmosphere the same effect of the sun, which is really next door. Okay, so one of these flare from a much closer magnetar could have some effect, yes, because
and it does remind us how interconnected we are with the rest of the galaxy, and even to some extent the universe beyond our galaxy.
Yes.
So I guess just in terms of closing question or two, I'm curious, the search for FRBs, where is it going next? And then how will your team's work help us to maybe refine or advance our search for FRBs, whether in our galaxy or outside of our galaxy?
Well, of course, now the main line of research is try to find more events of this kind, more events in which we see both the radio and the high energy X and gamma ray radiation, because we want to understand the details, because this discovery provided a connection between FRBs and magnetars, but this supports this class of models, but there are many varieties of models that involve magnetars to produce FRBs, many different ones. And until we have more data on this, it is difficult to discriminate between these different possibilities. For instance, there are many models that predict that both the X-rays and the radio are produced close to the magnetar in the so-called magnetosphere. And there are other classes of models that predict that during these flares, the magnetar ejects a relativistic material that travels for a lot of larger distances and then crashes against something else, against, for instance, a previous material ejected by the magnetar, and the emission occurs there. Okay, so both models involve magnetars, but they are very different. Okay, right. For example, with integral, we could see in this particular event that the X-rays are delayed with respect of the radio by about 6 milliseconds. So it is something that has a meaning. I mean, is this something that will be seen also in other objects? Or maybe when we will have a larger sample, we will see that there could be any connection between the delays between radio and X-rays. You know, this kind of data are needed to discriminate between the different models. Another field of interest is why radio just from this burst and not from the other ones.
Right.
This burst was not particularly bright in X-rays. There have been bursts from this same object that were more luminous. The only possibly strange thing of this burst is that it was slightly harder. Harder means that there were more photons of high energy than usual. So maybe this could be a hint that could link this particular event and not the other ones with the radio emission. But of course, based on a single detection, it's very difficult to make prediction.
Right, right. So more work is needed to understand to what extent this single event is unique, or is maybe one of a kind of events that we're now at the point where we can detect them and we can study them.
Yes, yes.
Excellent. I want to thank you so much for joining us here at the Star Spot, Professor Sandro Mereghetti. Really appreciate your time today. Thank you for joining us. This was actually our first YouTube live version of the Star Spot. So
yes.
Thank you for helping me kind of inaugurate that. I really appreciate it. I'd love to have you back on the show as more information comes in and we can get a bit of a deeper appreciation for these really mysterious FRB objects. For now, thank you so much. Appreciate your time.
Thank you for the invitation. Bye-bye.
Thank you. Bye now.